not to be confused with inequation. Less than and greater than redirect here, for the use of the less than and greater than signs as punctuation, see bracket. For the UK insurance brand, more th greater than n, see more than. In mathematics, an inequality is a relation that holds between two values when they are different. The notation of b means that a is not equal to b. It does not say that one is greater than the other, or even that they can be compared in size. If the values in question are elements of an ordered set, such as the integers or the real numbers, they can be compared in size. The notation a less than b means that a is less than b. The notation a greater than b means that a is greater than b. In either case, a is not equal to b. These relations are known as strict inequalities. The notation a less than b may also be read as a is strictly less than b. In contrast to strict inequalities, there are two types of inequality relations that are not strict. The notation of b means that a is less than or equal to b. The notation of b means that a is greater than or equal to b. An additional use of the notation is to show that one quantity is much greater than another, normally by several orders of magnitude. The notation of b means that a is much less than b. The notation of b means that a is much greater than b. Properties. Inequalities are governed by the following properties. All of these properties also hold if all of the non-strict inequalities are replaced by their corresponding strict inequalities, and monotonic functions are limited to strictly monotonic functions. Transitivity. The transitive property of inequality states, for any real numbers a, b, c, if a b and b c, then a c. If a b and b c, then a c. If either of the premises is a strict inequality, then the conclusion is a strict inequality. E.g., if a b and b greater than c, then a greater than c. An equality is of course a special case of a non-strict inequality. E.g., if a equals b and b greater than c, then a greater than c. Converse. The relations and are each other's converse. For any real numbers a and b, if a b, then ba. If a b, then ba. Addition and subtraction. A common constant c may be added to or subtracted from both sides of an inequality. For any real numbers a, b, c, if a b, then a plus cb plus c and a minus cb minus c. If a b, then a plus cb plus c and a minus cb minus c, i.e., the real numbers are an ordered group under addition. Multiplication and division. The properties that deal with multiplication and division state, for any real numbers a, b and non-zero c. If c is positive, then multiplying or dividing by c does not change the inequality. If a b and c greater than 0, then ac b c and a, c b, c. If a b and c greater than 0, then ac b c and a, c b, c. If c is negative, then multiplying or dividing by c inverts the inequality. If a b and c less than 0, then ac b c and a, c b, c. If a b and c less than 0, then ac b c and a, c b, c. More generally, this applies for an ordered field. See below. Additive inverse. The properties for the additive inverse state, for any real numbers a and b, negation inverts the inequality. If a b, then minus a minus b. If a b, then minus a minus b. Multiplicative inverse. The properties for the multiplicative inverse state, for any non-zero real numbers a and b that are both positive or both negative. If a b, then 1, a 1, b. If a b, then 1, a 1, b. If one of a and b is positive and the other is negative, then, if a less than b, then 1, a less than 1, b. If a greater than b, then 1, a greater than 1, b. These can also be written in chained notation as, for any non-zero real numbers a and b, If 0 less than a b, then 1, a 1, b greater than 0. If a b less than 0, then 0 greater than 1, a 1, b. If a less than 0 less than b, then 1, a less than 0 less than 1, b. If 0 greater than a b, then 1, a 1, b less than 0. If a b greater than 0, then 0 less than 1, a 1, b. If a greater than 0 greater than b, then 1, a greater than 0 greater than 1, b. Applying a function to both sides. Any monotonically increasing function may be applied to both sides of an inequality and it will still hold. Applying a monotonically decreasing function to both sides of an inequality means the opposite inequality now holds. The rules for the additive inverse, and the multiplicative inverse for positive numbers, are both examples of applying a monotonically decreasing function. If the inequality is strict and the function is strictly monotonic, then the inequality remains strict. If only one of these conditions is strict, then the resultant inequality is non-strict. The rules for additive and multiplicative inverses are both examples of applying a strictly monotonically decreasing function. A few examples of this rule are exponentiating both sides of an inequality by n greater than 0 when a and b are positive real numbers, a b and bn, a b a minus n b minus n. Taking the natural logarithm to both sides of an inequality when a and b are positive real numbers, a b lane lane, a less than b lane less than lane. This is true because the natural logarithm is a strictly increasing function. Ordered fields. If is a field and is a total order on F, then is called an ordered field if and only if a b implies a plus c b plus c. 0 a and 0 b implies 0 a times b. Note that both an are ordered fields but cannot be defined in order to make an ordered field, because -1 is the square of I and would therefore be positive. The non-strict inequalities are non-real numbers are total orders. The strict inequalities less than and greater than non-real numbers are strict total orders. Chained notation. The notation a less than b less than c stands for a less than b and b less than c, from which, by the transitivity property above, it also follows that a less than c. Obviously, by the above laws, one can add, subtract the same number to all three terms, or multiply, divide all three terms by same non-zero number and reverse all inequalities according to sign. Hence, for example, a less than b plus e less than c is equivalent to a minus e less than b less than c minus e. This notation can be generalized to any number of terms. For instance, a1 a2, and means that I plus 1 for I equals 1, 2, n minus 1. By transitivity, this condition is equivalent to IAJ for any 1 IJN. When solving inequalities using chained notation, it is possible and sometimes necessary to evaluate the terms independently. For instance, to solve the inequality 4x less than 2x plus 1 3x plus 2, it is not possible to isolate x in any one part of the inequality through addition or subtraction. Instead, the inequalities must be solved independently, yielding x less than 1/2 and x minus 1 respectively, which can be combined into the final solution minus 1x less than 1/2. Occasionally, chained notation is used with inequalities in different directions, in which case the meaning is the logical conjunction of the inequalities between adjacent terms. For instance, a less than b equals cd means that a less than b equals c, and cd. This notation exists in a few programming languages such as Python. Sharp inequalities. An inequality is said to be sharp if it cannot be relaxed and still be valid in general. For instance, suppose a is a real number, then the inequality a20 is sharp, whereas the inequality a2-1 is not sharp. Inequalities between means. There are many inequalities between means. For example, for any positive numbers a1, a2, and we have hgaq, where power inequalities. A power inequality is an inequality containing ab terms, where a and b are real positive numbers or variable expressions. They often appear in mathematical Olympiads exercises. Examples for any real x. If x greater than 0, then. If x1, then. If x, y, z greater than 0, then. For any real distinct numbers a and b. If x, y greater than 0 and 0 less than p less than 1, then. If x, y, z greater than 0, then. If a, b greater than 0, then. This inequality was solved by Iolani in JSTOR, Volume 97, Number 1, 1990. If a, b greater than 0, then. This inequality was solved by S. Manyama in AJMA, Volume 7, Issue 2, Number 1, 2010 and by V. Sertoaj in JNSA, Volume 4, Issue 2, 130-137, 2011. If a, b, c greater than 0, then. If a, b greater than 0, then. This result was generalized by R. Ozols in 2002, who proved that if a1 and greater than 0, then. Well-known inequalities. Mathematicians often use inequalities to bound quantities for which exact formulas cannot be computed easily. Some inequalities are used so often that they have names. Azuma's inequality, Bernoulli's inequality, Buell's inequality, Cauchy-Schwarz inequality, Chebyshev's inequality, Chernoff's inequality, Kramnik-Utarau inequality, Hoeffding's inequality, Holder's inequality, inequality of arithmetic and geometric means, Jensen's inequality, Kolmogorov's inequality, Markov's inequality, Minkowski inequality, Nesbit's inequality, Pedo's inequality, Poincaré inequality, Samuelson's inequality, triangle inequality, complex numbers and inequalities. The set of complex numbers with its operations of addition and multiplication is a field, but it is impossible to define any relation so that becomes an ordered field. To make an ordered field, it would have to satisfy the following two properties. If a b then a plus c b plus c. If 0 a and 0 b then 0 a b. Because as a total order, for any number a, either 0 a or a 0, in either case 0 a2, this means that and, so and, which means contradiction. However, an operation can be defined so as to satisfy only the first property. Sometimes the lexicographical order definition is used, a b if less than or. It can easily be proven that for this definition a b implies a plus c b plus c. Vector inequalities. Inequality relationships similar to those defined above can also be defined for column vectors. If we let the vectors, we can define the following relationships. If a, and, if a. Similarly, we can define relationships for, and. We note that this notation is consistent with that used by Matthias Eggart in multi-criteria optimization. The property of trichotomy is not valid for vector relationships. For example, when and there exists no valid inequality relationship between these two vectors. Also, a multiplicative inverse would need to be defined on a vector before this property could be considered. However, for the rest of the aforementioned properties, a parallel property for vector inequalities exists. General existence theorems. For a general system of polynomial inequalities, one can find a condition for a solution to exist. Firstly, any system of polynomial inequalities can be reduced to a system of quadratic inequalities by increasing the number of variables and equations. A single quadratic polynomial inequality in n-1 variables can be written as, where x is a vector of the variables and A is a matrix. This has a solution, for example, when there is at least one positive element on the main diagonal of A. Systems of inequalities can be written in terms of matrices A, B, C, etc. And the conditions for existence of solutions can be written as complicated expressions in terms of these matrices. The solution for two polynomial inequalities in two variables tells us whether two conic section regions overlap or are inside each other. The general solution is not known, but such a solution could be theoretically used to solve such unsolved problems as the kissing number problem. However, the conditions would be so complicated as to require a great deal of computing time or clever algorithms.